Okay, this is Brian Washburn here. What I want to do is solve the equations of motion for linear air resistance that we derived last time. What I have is I have two equations. I have an equation for the equation number one is the rate of change of the x component of the velocity is equal to minus a constant times the velocity itself, the x component of velocity, and then the rate of change of the y component is equal to g minus a constant times vy. Okay, so what I want to do is I want to solve each of these equations for the x and y components of velocity. So let's first solve equation 1 for Vx as a function of time. Okay. Now there's two ways I can do this. I could use direct integration. I could just integrate equation 1, but I'm going to use the second method. I'm going to just guess a solution because it's pretty straightforward first order differential equation. So basically, equation 1, if I read it, says the first derivative of this function here is equal to a constant times the function itself. All right. Functions that you take a derivative and you get the same function are exponential functions. So my guess is going to be v of t is going to be equal to of x is going to be equal to a e to the minus kt. And I need to get a and t. Now, in order to do this, I have to have an initial condition. Okay. And the initial condition is that at times t equals 0, Vx is equal to Vx is 0. Okay. So I'm going to use equation 1 and equation 3 to get a and x. Okay, so let's first get a. So using my guess and equation 3, I can say that Vx is 0 into the guess is going to be equal to a e to the 0. Okay, but that's equal to a. But from equation 3, v of 0 has to equal v naught. So that implies that v naught x is equal to a. Okay, so now we can write down my guess. Vx is equal to v naught x e to the minus kt. Okay, so now we have a. All right, so let's call that a 4. Now, let's take this 4 and stick it into equation 1. Okay, so I can say that Vx dot, using equation 4, v naught x minus kt. Oh, sorry, just not kt, but just k. Okay. And then I get e to the minus kt. I can rewrite this equation as minus k times v naught x e to the minus kt. For that equation, just writing out all like that, v naught is equal to minus k v naught. Okay. Now if you take a look at, let's call that 5. If you compare this equation with 1, we can say that k is equal to minus b over m. All right, so let's write that again. Okay, so then my final solution is v of x is equal to v x naught e to the minus b over m times time. That I'm going to call that equation. That is my equation. That is my solution. Okay. So I'm going to copy that. Now let's just move to the next page here. Okay. Well, I have it here. Okay. Let me just erase that. Okay, and let me just paste it. Okay, all right, so that's what I got. Okay, now let's plot that function. Okay, so that function, basically, we want to plot it. Oops, sorry, let's do this. So let's make a plot of that. So we have time v, and it's an exponentially decaying function. So if this thing here is, let's apologize for that. It's harder to just draw a straight line once in a while. All right, there we go. Time. So it's going to start from here, and so it's going to start from there, and then what we're going to do is exponentially decay down. Okay, where this is Vx naught. So what that means is in the projectile motion is since the only force acting on it is in the x direction, and that is due to air resistance, and it's always resistive, it's going to cause the x component to go to 0 and stop. Now once it's stopped, air resistance isn't going to speed it up and increase that component anymore. Okay. All right. Now if I want to solve for, once I have that, I need to solve for position as a function of time. What I need to do is solve x at time. Okay. And I can do that by direct integration, just recognizing that dx dt is equal to Vx. I can say x is a function of time is equal to the integral, okay, from my initial time to some arbitrary time t, okay, of Vx, okay, t dt. Okay, so that, now I'm going to take the integral of basically an exponential function. That's going to give me another exponential function. Now, the one, just kind of following the way your book does it, your book recognizes that there's some initial position, right? So that x at, for example, there's some initial position x naught. So I can rewrite this as x minus x naught is equal to the integral of Vx t prime, where t prime is just some constant of integration. I'm going to integrate that from 0 to the time t, and then actually this guy should be t here. Okay. If I do that, what I'm going to get is x as a function of time is going to be equal to my initial position, x naught, times what I had before, 0 to t, and I'm going to put in the solution I wrote before, Vx naught e to the minus t, and then I can't forget the constant b over m. That's what we had there. Okay, and if I integrate that, I'm going to get here, I can just say I'm going to get, well, x naught, and then I'm going to get here minus v naught, okay, then b over m over b, okay, and then I'm going to get here e to the b over m t, okay, and so then that's my solution. So I get another exponential decay there. All right. Now, one thing, looking at your book talks about this. It writes the solution for the velocity as a function of time like this. It says it's going to be equal to x naught e to the t over, it calls this tau, where tau is defined as m over b. Okay. Now, why does it do that? So what is tau? Tau is kind of a decay constant, if you remember these exponential functions. Basically, if you wait a time t, time tau, which is equal to m over b, the speed decreases by 1 over e. Basically, if you set t equal to tau, you're going to get minus 1, and so then v naught decreases by, goes from v naught to v naught times e to the minus 1. And so that's basically what the speed would be after one time constant. Okay, so that's the exponential decay. All right, so now what we want to do is we want to solve for the next equation. The next equation is that guy there. So we want to solve for the x component. Let's go to this slide here. See if that works. Okay, I'm going to put that here. Okay, so I want to solve that equation, equation 2. All right, now notice again, it looks just like equation 1, except I have a constant. Okay, so I have a constant there. However, we can look at this equation in a little bit more physical way, and we can solve the equation. We can just directly integrate or guess a solution, but let's look at this equation in terms of a concept we're going to call a terminal speed. Okay, so let's look at terminal speed. And I think you're familiar with this concept. If you jump off an airplane, eventually you're going to stop accelerating and reach the maximum speed and stay there. So if you stop accelerating, that means that Vx dot is equal to 0. That's 0 acceleration. That means that looking at equation 2, g must equal to b over m times v, and I'm going to call that the terminal velocity. Obviously, it's in a y direction. Okay, so I can solve for the terminal velocity. The terminal velocity is going to be equal to mg divided by b. Okay, and that's let's get rid of, sorry about that. So that's my terminal velocity. I'm going to So I'm going to use that in my solutions, okay? In fact, I'm going to write equation 2 equation 2 in terms of that terminal velocity, okay? So how can I do that? Well, so I can write, if I write this as mv dot mg bvy, what we had before, okay? I can say that mg over, I can write this as mvy dot is going to be equal to, well, mg, using this equation, I can see that mg is equal to b times v term. Okay, so that means that I have b v term here minus b vy. So then I have here b, okay, and then I'm just going to pull out a minus sign, and then I'm going to have vy minus v term. Okay, and that's a nice equation. Let's call that equation, let's call it equation 5. Okay, so it says that the rate of change of the y component of the velocity is equal to minus a constant times that difference, where v term is a constant. Okay, so we can make another guess for a solution. Instead of guessing, I mean, again, what do we want to solve for? We want to solve for vy as a function of time. But let's make a guess. Instead of solving for vy, let's solve for vy minus v term, since that's just a constant. And it's going to be equal to, well, again, expect an exponential decay, all right? And so I can write something that looks like that. Okay. And again, I have to have initial conditions. Or what are my initial conditions going to be? That vy of 0 is going to be equal to vy naught. Okay? All right. And so if I use, so then this is my guess, just like what I did before. And now I can do the same procedure using the initial conditions and the differential equation I have above. For example, like we can say that vy of 0 minus v term is equal to a, which is equal to vy naught minus v term. Okay. Did I do that right? Yeah, I did that right. So that allows me to solve for a. Okay. So from that expression, that's pretty easy, but I can say that a is equal to vy naught minus v term. So sticking that back into my solution. Okay, my solution now, using this is Vy. Sorry about that. So now we have A. Okay. And then what we can do then is you can take that and stick that into the differential equation and solve again. And if you do that, we can get a final solution that Vy, as a function of time, is going to be equal to Vy naught e to the minus, again we got this k, what s is going to again just be b over m, b over m t, and then we have b term 1 minus e to the t b over m t. Okay, so that's my solution to my y component. Okay. Now one way we can check this is by saying, okay, let's look at the solution as t goes to infinity. As t goes to infinity, what I expect Vy to go to v term. Okay, and does that happen? Well, as t goes to infinity, this term goes to 0, this term goes to 0, and so the only term that's left is v term times 1. So that's what happens there. Okay, so that's at least what happens. Okay. Now, if you just take an object and drop it, all right, if you say an object and drop it, so that's the simplest. That's another very simple case. Let's actually take a look. We can actually do this. So say I just take an object and drop an object. So if I drop an object, I have this object. This, what I can do is, let's write down the initial conditions. If I drop an object at Vx naught is equal to 0, Vy naught is equal to 0. Okay, so going back, what I had here, well, if this is equal to 0, that means that obviously that Vx as a function of time is equal to 0. Okay, that's not very interesting. But then going back to my equation I have here, Vy as a function of time is going to be equal to, well, the first term here is 0. And then here I have v term 1 minus e to the minus b over m. That. Okay. So if I were to make a plot of Vy as a function of time, again, I apologize for that. Try to draw that straight. Okay. Time, and then this is Vy. It's going to start off at 0, and then exponentially reach v term here. Okay. If we want to solve for y as a function of time, okay, so what I can say is that dy dt is equal to Vy. That means that y as a function of time is going to be equal to, well, actually let's put y minus y naught is going to be equal to the integral of this. Use some variable of integration from 0 to time t right there. Okay, and you can easily integrate that. If you integrate that, you can see that v of y is going to be equal to v term y, v term t plus Vy naught minus v term. Okay, and then there's b over m. Is that right? Yeah. No, m over b, I should say. That's m over b. And then I have here 1 minus e to the b over mt here. Okay. All right. Okay. So that's all I have to say about that. Again, what we get is looking at these solutions, we get exponential decreasing solutions. Actually, one kind of cool thing. Notice what we did was we expressed everything in terms of this terminal velocity. And in some respects, that's kind of, knowing what the solution is and using that to express the solution. But it's a good thing to do because it writes in terms of something physical. We could, instead of having v term, we could have, just kept everything in terms of mg over b and having the equations in mg and b, but then you don't really get enough physics from it. If you write things in terms of v term, you see exactly that after the long time behavior goes to something you expect, a terminal velocity, instead of something that's just mb over v. Also, the units work out pretty well too. Notice that v term, so this is, let's take a look here. Notice that if we look at this equation here, this is velocity on this side, this is velocity, and this is a constant. So writing in terms of velocity is an easy way just to check, hey, my solution looks okay. This is unitless, this is a constant, this is a velocity, or this is his units of velocity. That's a good check. And even in this equation here, you have velocity times time, that's a position. You have a velocity times m over b. What's the units of m over b? Well, notice that remember the argument of an exponential always has to be unitless. So if this is t, b over m has to have units of 1 over t, and then m over b has to have units of time. So again, this is velocity, meters per second times second. That gives me meters, and that gives me meters as my solutions. So it's a sophisticated way of writing a solution. All right, so that's it. We'll talk to you later. Take care. Bye-bye.